All right, let's jump right in. We're here to talk about a climate solution that might just be hiding in plain sight. It's a real powerhouse, and it's gaining some serious momentum in the toughest industries out there. We're talking about the rebirth of a true workhorse, the internal combustion engine. But this time, it's running on hydrogen.
So let's get right to the point, the bottom line of this whole analysis. The hydrogen internal combustion engine, what we call H2ICE, it's not some science project anymore. It's not just a what if. For the really tough jobs in our economy, it has graduated to become a core part of a real, workable decarbonization strategy.
Okay, so here's our core assertion, our strategic take for heavy industry. It's pretty simple, really. When you look at the most demanding applications out there, think construction, agriculture, mining, long-haul trucking, H2ICE emerges as the most practical, no-nonsense way to get to zero emissions.
And this is the really critical strategic point. Why is it so pragmatic? Because it's an evolution, not a complete tear-it-all-down revolution. We're tapping into a massive industrial base, an entire supply chain that's been perfected for over 100 years. That means we can move faster, and it's way more cost-effective because we're not starting from zero.
Now, to really get why H2ICES is such a compelling option, we've got first to understand the problem it's designed to solve. And let me tell you, when it comes to heavy industry, the challenges are, well, they're immense.
This is the question everyone asks, right? If batteries are the future, why not just electrify everything? And it's a fair question. The thing is, the demands of heavy industry are just a different beast altogether. Look, battery electric tech is fantastic for a lot of things, but it starts to hit a wall when you throw the brutal realities of heavy-duty work at it.
And this really spells out what that brutal reality looks like. We're talking about massive power and torque. We're talking about machines that live in harsh, dusty, high-vibration environments. You've got remote locations with no grid for miles. And you absolutely need to refuel fast right there on site. Plus, you can't sacrifice your payload. Downtime for charging for hours? That's just not an option.
So when you lay it all out like this, the trade-offs become crystal clear. Look at refueling time, hours for a battery versus minutes for both hydrogen options. But then look at environmental robustness. This is a big one. Fuel cells, they have these sensitive membranes that just don't like dust. And batteries, they're heavy, which eats into your payload. The H2ICE, though, at its heart, it's still an internal combustion engine. It's built tough. It can handle the dirt and the grit, and that's why it's just a better fit for these kinds of jobs.
Okay, so how do we get here? How did this become a viable option? It's really important to get this. We are not just talking about an old diesel engine that we've jury-rigged to run on hydrogen. No way. This is a sophisticated piece of tech, and it's all thanks to a couple of major breakthroughs that completely changed the game.
So breakthrough number one was all about how you get the fuel into the engine. The old way, port fuel injection, or PFI, was a real problem. You're mixing hydrogen and air before they get to the cylinder, which led to low power and, even worse, the risk of a nasty backfire. The big leap forward is direct injection, or DI. We now shoot the hydrogen directly into the cylinder at just the right moment. This completely solves the backfire issue and gives us a huge boost in both power and efficiency.
And here's the second game changer, mastering what we call the ultra-lean burn. Now, hydrogen has a bit of a reputation for burning really hot, and that heat used to create a ton of nasty NOx emissions. But here's the elegant solution engineers figured out. Hydrogen is happy to burn with a huge amount of extra air, so you can flood the cylinder with way more air than you need for combustion. This massive surplus of air actually acts like a coolant inside the cylinder, lowering the temperature and stopping NOx from ever even forming. It's a brilliant way to solve the emissions problem right at the source.
So let's just put a number on the climate benefit, shall we? We're talking about a 99.9% reduction in CO2 emissions from the tailpipe. The main thing coming out is just water vapor. Yeah, there's a tiny trace from burning a bit of engine oil, but that's it. And this is so important. That performance is why H2IC now officially meets the definition of a zero-emission vehicle technology under the European Union's toughest new standards. It's officially in the club.
All right, so the tech is impressive, for sure. But honestly, the business case might be even more compelling. The economics of this, for the companies buying the equipment, for the supply chains, for whole industries, this is where H2ICE really starts to shine from a strategic perspective.
Just look at the upfront cost. This is huge. An H2ICE vehicle costs just a little more than the diesel engine it's replacing. But compare that to the alternatives. You're looking at being up to 31% cheaper than a fuel cell system, and you're completely avoiding the massive cost of batteries for a heavy-duty electric vehicle. For a fleet operator, that is a much lower barrier to making the switch.
And this is why those costs are so much lower. Look at that chart. 90% of the components can come from the existing diesel engine supply chain. That's not just parts, that's factories, that's suppliers, and most importantly, that's skilled jobs. We get to leverage and repurpose the incredible manufacturing base we already have. We protect our industrial core while we decarbonize. It's a powerful combination.
And here's another massive strategic advantage: supply chain security. Think about it. This whole approach completely sidesteps the rat race for critical minerals like cobalt and lithium for batteries, or the expensive platinum group metals needed for fuel cells. We're talking about avoiding huge geopolitical risks and resource bottlenecks. It just fundamentally de-risks the entire transition to zero emissions.
Okay, so what does the path forward look like? How do we get to mass adoption? Of course, there are still hurdles to overcome, but the key thing to understand is that we're talking about engineering and policy challenges now, not some fundamental scientific roadblock we don't know how to solve.
Really, the challenges boil down to two main things: packaging and logistics. On the vehicle, it's about finding the best way to integrate the hydrogen storage tanks. And on the ground, it's about figuring out the logistics of refueling on a remote worksite. Now, these are not simple problems, but they are absolutely solvable engineering problems. And we're already seeing great solutions, like clever chassis-integrated tank designs and mobile refueling units that companies like JCB are already putting to work in the field. Which brings us to what is probably the single biggest hurdle left and has nothing to do with engineering. It's policy. We need official, widespread recognition of H2ICE as a zero-emission technology. That single step would send a powerful signal to the market. It's the green light that unlocks serious investment, helps align regulations, and really kicks the whole thing into high gear. So, let's leave it with this final thought. In this massive global push for brand new, revolutionary technologies, is it possible that we've been overlooking one of the most powerful solutions, one that's been hiding in plain sight all along? Maybe, just maybe, the fastest path to a zero-emission future is actually an evolutionary one that builds on the incredible foundation we've already perfected.